Excellent. Now let me try this. Voidburner is recording this call. Ah! Okay. Okay, this is recording right now. I'm going to bring up your Skype, your view, so let me just... hold on. View. Share your screen. Alright. Now, do you see what I see? Hello?
And there's my presentation.
You see it? Mosaic? Hello?
Hello?
Can you hear me?
Yes, can you hear me?
I can hear you. Okay. Can you run me through kind of a basic quick thing of your PowerPoint?
Sure.
All right. Now, NMR spectroscopy. What is it?
NMR spectroscopy.
What is it?
NMR spectroscopy is a technique that allows you to see the structure of molecules. So it will tell you how the bonds are set up. And it does so by studying the spin states, which are induced by magnetic fields. If you go to... What's going on?
Hold on, sorry. Okay.
If you look at the picture on the figure 1, that will tell you how the atoms spin up. And then, can you see it?
Yeah.
Yeah. All right. On the next slide, you find out that you have two spin states, alpha and beta, and that is caused by a radio frequency electromagnetic field created by the spectrometer, which is going to be measuring the transition of the nuclei between the alpha and the beta state.
Ah.
Following me so far?
Yep. So.
And the spectrometer would run in two settings, in 300 megahertz and 500 megahertz.
Right.
Also, once it has this reading, it will tell you the chemical shift of the molecule. And as it says in the PowerPoint, chemical shift is the frequency of resonance in comparison to molecular standard.
All right. So this is a XY coordinate system. A geography, y-axis, intensity.
Yeah, to be zero chemical.
So is this what I was referring to?
So
this is the axis.
The reason why we set up that way is like what?
What I'm looking at right now, the chemical shift. Is that what I was referring to? Okay. So based on a position on the grid.
Mm-hmm.
Okay.
Mm-hmm.
Okay, I think I get that. All right.
Yeah. Yes. Yeah, and we do it that way so that if you take the reading of a molecule in one spectrometer, it doesn't change if you use a different machine. Okay. Figure 3 is an example of how the NMR reading looks like.
All right. See that. So figure 4 is...
Figure 4 will tell you, tells you how we also make electrons to spin, and the spin of the electrons make their own magnetic field, which counteracts the magnetic field that is being applied to the nuclei, which makes it harder for the machine to detect the nuclear itself. So it's like putting up a shield.
Cool.
Cloak. Yeah. And so it becomes a battle between the magnetic field created for the spectrometer and the magnetic field created of the electrons. It's kind of like a defending the castle kind of deal.
Oh, interesting.
And
this whole thing is kind of a chemical.
Mm-hmm.
Right. So electron activity, pi bonds.
And electron activity refers to how certain atoms tends to attract electrons more than other atoms does. And this causes your target nuclei to have less electrons. So that shield that it creates is weaker. And so the machine has an easier time reading it.
Right.
And your pi bonds are specific kind of bonds, which are...
They de-shield?
Yeah, they de-shield. And by de-shielding, I'm referring to diminishing the magnetic field created by electrons. And so those terminal alkynes, however, will shield up the atom. It's kind of funny because the only difference between a pi bond and terminal alkenes is an extra set of pi bonds. So one set of pi bonds will de-shield it, but two of them will shield it back up.
Oh, so in very close layman's terms, it's kind of like two negatives make a positive.
Yeah.
Negative. So yeah, an additional one.
Yeah.
Okay.
That's exactly right.
All right. So standard is the following are CH greater than CH3, carbon slightly more oxygen than hydrogen, and other chemicals similarly. Interesting.
Yeah.
Now, what is coupling?
Coupling, what happens is that when you got atoms, nuclei of different chemical shapes next to each other, it makes the signal that the NMR perceives split up.
Oh, that's what that diagram shows right here.
Yes. So that instead of you getting one single peak, like you saw back in figure 3, I believe, you get like 2 peaks per atom. And the order and the common patterns are explained in slide 3. You get your doublets, which are 2 peaks, your triplets, which are 3 peaks, and your quartet, which are 4 peaks of different ratios.
Wait, slide 3?
Yeah, 13.
13?
Mm-hmm.
Oh, I thought you said 3. Okay, let me go check out. 13. 11. Okay. General rule. Okay, doublet, triplet, quartet. 3.
Yeah, and the next slide will tell you the ratios of the intensity of those peaks. So if you look, for example, the doublet, on the second floor, counting from top to bottom, so it's a 1-to-1 ratio. So the peaks are all have the same intensity or the same height, for that, if you will.
Right.
Then if you make it into a triplet, and you will get 3 peaks. 2 of them will be of the same ratio, and then the second one in the middle will be like twice the height.
Awesome.
And it will keep going in that order until step, which is
they add together 1,
which is,
1,
I think
2,
is the highest that you can get.
2, 1, 3, 3, 1, 4, 4, 1, 5, then 6, 4, 10, and 3, 3, 6. Oh, okay. Pascal's triangle. Okay.
Pascal's triangle, that's what it's called.
Yep.
If you go to slide 15, you will get a visual on what coupling looks like in an NMR reading. See how the peaks are not one single peak is actually split.
I didn't catch that last part.
Yeah.
What did you say? I didn't catch that last part.